Hi everyone. Today I'll be talking about a topic that I'm very much excited about, and that's the topic of string theory and its spectrum. So, for that, let's go back first to the motivation, namely why string theory remains a very attractive theory to this day and why its spectrum is worth studying. Right. So let's go back to actually how string theory was born. At the time, the community was thinking about four-point amplitude. So think of a scalar theory, a theory of a scalar field, and in particular, two-to-two scattering in this theory. So two particles come, interact, and give two particles of the same theory. Now, if this particle does not couple to other fields in this theory, then the amplitude is well behaved at high energies. However, if we allow for the possibility of exchange of a particle of spin j in this propagator, then the amplitude diverges at high energies. And even if you try to allow for the possibility of exchange of very high spin, so some particles up to subspin J max, then still the amplitude diverges at high energies. However, if you allow for that sum to go up, the upper bound of that sum to go to infinity, then you can get an amplitude that behaves well at high energies. And this is exactly how Veneziano came to postulate this amplitude for a four-point amplitude of four scalars. Namely, now you see this gamma function over here, this ratio of products of gamma functions, where now, because of the fact that the gamma function has infinitely many poles, we see that there is a possibility of exchange in the scalar amplitude of infinitely many states with arbitrarily high spin and mass. And very soon after, it was recognized that this amplitude is, in fact, an amplitude of a theory that's not a field theory anymore, but instead a string theory, namely the theory of a propagating string that sweeps out a two-dimensional worldsheet in some d-dimensional spacetime in which it propagates. And that string has infinitely many states, and there is a fundamental scale associated to the string, the so-called alpha prime, the string scale, which is a free parameter in each dimension full. So Veneziano, by postulating this amplitude, gave birth to a string theory with infinitely many physical states, the mass square of all of which is set by the inverse string scale alpha prime. And so the integer in front, the factor of proportionality in front, it's always an integer that depends on the theory, the particular theory in question. So for example, for the open bosonic string, this integer is n minus 1, where n starts from 0 and can go up to infinity. Now, all these states, they're associated with polarization tensors, and those polarizations are always transverse and traceless for the states to be physical, which means that they can be associated with irreducible representations of the little group of the spacetime Lorentz group. So it's SOD minus 1 or SOD minus 2, or depending on whether the states are massive or massless, respectively. So in principle, all allowed tensor symmetries are possible in the spectrum, and let's consider the open bosonic string case, and in particular, the subclass of symmetric tensors. If we look at so symmetric tensors of spin S, so if we look in that case at the plane spin alpha prime m squared, so spin and mass squared, well then the states, if we just depict in this diagram the states in terms of their spin and mass, they're organized in trajectories. In trajectories, namely where the spin increases linearly with m squared. So for example, here we have the so-called leading Regge trajectory. And as the mass square grows, we have more and more, if we want, subleading Regge trajectories. And they're all linear. Now, what does the spectrum look like still for the case of the open bosonic string if we decide to depict the states in terms of the Young diagrams that correspond to the irreducible representations in question? So in that case, here we have the column, in this column we have the level, the mass level n, which starts from 0, as we discussed, and can grow up to infinity. And in the respective rows, you see the decomposition in terms of physical states of every mass level. So what do Young diagrams in general look like? They're a set of boxes. Each box corresponds to one spacetime index of the respective polarization tensor of the state. In this setting, in this presentation, I'm using the symmetric base, namely boxes that are put in the same row are symmetrized, correspond to symmetrized indices, and there might be relations between boxes of different rows. So for example, here at level 0, there's only one state, the famous tachyon, of which actually the 4-point amplitude of the Veneziana 4-point amplitude is corresponds to the scattering of 4 tachyons in this context. And then we have the only massless state of the open bosonic string, that is a vector. So it's the only SOD minus 2 representation, and one vector means one index in the polarization, so one box. And then we have the symmetric rank 2, so it's a massive spin 2 state. And then as the level grows, we see mixed symmetric states, so states with mixed symmetry. We also see non-trivial multiplicity. And more generally, as the level increases, rows the number of rows increases, and then patterns become more complex that we see. However, already at this point, we can make a crucial observation, namely that there is a kind of repetition. So here in red, you see, for example, the leading Regge trajectory, so the set of highest spin states per level, the set of symmetric tensors that are also the highest spins of their respective levels, so spin S at level S. But over here in orange, you see the first clone, so to speak, of the leading Regge. So it's a truncated clone. It starts with a massive spin 2, but then it increases arbitrarily high in mass and spin as the level increases. And so, based on all this information, it's clear that these infinitely many massive higher spins in the string spectrum, they're not just an artifact of string theory, but rather they're crucial to its celebrated property of string for UV softness. And so they lie precisely at the origin of the good UV behavior of string amplitudes. And so it's important to try to understand them even better, even more thoroughly. And for that, before I move to my own research, let's review very quickly the old ways, the traditional ways of constructing the spectrum of the string. So essentially, there's four. There's the old covariant way where essentially you need to choose, you need to move on a level by level basis. So recall that any string state we can think of as a function of the creation operators alpha minus 1, alpha minus 2, and so on among the string oscillators. So mu here is always a spacetime index. So implicitly, I'm thinking of the string field x mu, with which one writes the Polyakov action, and then because of its equation of motion, you expand it into Fourier modes, namely the string oscillators, and among them, those with negative modes over here correspond to the creation of oscillators, and the positive ones to the annihilation ones. And so this means that a general string state is a function, it's a polynomial, essentially, of the string creation oscillators, creation modes, contracted with respect to their spacetime indices with the indices of the state's polarization tensor. And so in the old covariant way, you start with the level, you decide which level you would like to probe, you write an ansatz for all possible oscillators that can be excited at the level, solve the Virasoro constraints on this ansatz. It suffices to solve only two, L1 and L2. The Virasoro constraints, namely, are the ones that impose physicality of states in this string theory, and in string theories more generally. And so once you solve these two constraints, you get, as a result, the decomposition of the spectrum into physical states. So not only their polarizations, but exactly what their polynomials look like on a level-by-level basis. To avoid having to solve the Virasoro constraints every time, the light cone method had been proposed a long time ago. There's a kind of different advantage in the sense that you bypass having to solve the Virasoro constraints, but this comes at a price, namely the construction is non-covariant. And so you have to recombine the SOD minus 2 representations that you built with this method into SOD minus 1 massive string states. So this method also has a limitation, namely it becomes harder and harder to use as the level increases. And then there's also the method of the DDF, so del giudice di Vecchia and Fubini, where a very high level of the string is accessible in the sense of calculating a string amplitude that corresponds to the scattering of a number of photons of an original tachyon. And this has been shown to be able to encode all the information as to what the states at that very high level look like. But again, this comes with a limitation that there's an arbitrary reference momentum that enters the formalism. And there's also the partition function of Cartwright and Thorne, and later of Forcella, Hanani, and Proust, where again, it becomes harder and harder to read off the content, the state content, as the level increases. And so just very quickly, let's recall how the all covariant wave, for example, has as output on a level by level basis the state content of in this particular case, the open bosonic string. Well, for the lowest level, n equals to 0, no oscillator can be excited. So we have an empty polynomial, just a vacuum that's a tachyonic state, because n minus 1 is minus 1 in this case, so we get m squared negative. And for n equal to 1, there is only one oscillator. It's contracted with an a priori arbitrary vector. So the scalar product is the vector in this d-dimensional spacetime in which the string propagates. And once you impose the Virasoro constraints on this ansatz, you get that this epsilon vector is transversed. So we get the massless, because n minus 1 is 0, the massless vector of the open bosonic string, the only massless state of the open bosonic string. Now, for n equal to 2, there's two terms that one can excite. Again, solving the Virasoro constraints, one finds out that there's only one massive state that propagates at this level. It's physical at this level and is a massive transverse and traceless spin 2 state. And in fact, all of these states are the lowest states, the lightest states of an entire trajectory I was referring to in the previous slides, namely the leading Regge trajectory of spin S states at level S. So we have a symmetric rank S tensor, whose indices are contracted with S copies of alpha minus 1, and imposing physicality on this entire trajectory, namely that the L1 and L2 constraints are satisfied, one derives that the epsilon tensor is transverse and traceless. And so a bit on the interactions at this point. Well, the massless vector and the massless spin 2, now of the closed string, they have for a long time been known to reproduce at low energies the interactions of the Yang-Mills and Einstein-Hilbert actions, famously. So in fact, these 2 points, they still serve as motivation in favor of studying string theory further. So the fact that the massless graviton of GR is a state that appears in the closed string spectrum that also reproduces the interactions of the graviton of GR. Then, as far as the massive spin 2 states are concerned, I showed with Dieter Luster, Stefan Stieberger, and Puri Maslumi that some of the lightest massive spin 2 states, perhaps surprisingly, they can reproduce, at least to lowest order, the cubic vertices of a theory known as bimetric theory, which is an extension of GR in the sense that in its spectrum it contains a massless graviton, but also a massive spin 2 state. But that theory has a parametric scale separation, so in principle, one would not expect that a string theory of infinitely many massive states, and thus infinitely many massive spin 2 states, all relevant at the string scale alpha prime, would be able to reproduce the interactions of a field theory. Nevertheless, we showed that this is possible in a work that I initiated and led. A bit more is known about the leading Regge trajectory in the seminal paper by Sagnotti and Tarona for the case of the bosonic string, and in work by Oliver Schlotterer for the case of the superstring. But the main point is that little is known about all these subleading Regge trajectories. Every method that I referred to in the previous slides comes with its own limitation. And the main challenge is, what do excited string states look like? So what does a state very deep in the spectrum look like? And whether there's a certain pattern which could somehow be concealing a bigger organizing symmetry inside the string spectrum. So for that, let's go back to the definition of irreducible, essentially SOD minus one representations. So more generally, let's start with GL irreducible representations. So such a general representation we can depict either by a polarization tensor of this type. So it has symmetric groups of indices separated by commas from each other. So in this first group, we see S1 symmetric indices mu. That's what the notation mu parenthesis S1 stands for. And here we have another such symmetric group and so on and so forth. And those groups we can associate to rows. So for example, a row of S1 symmetric boxes, so this is the length of the first row, corresponds to the first group of symmetric indices and so on and so forth. And this all in the symmetric base. There's also the anti-symmetric one. They're both equally, one can use equally well either of the two. So the point is that for a GL irreducible representation, this diagram, apart from having either symmetric rows or being in the anti-symmetric base, so having anti-symmetric columns, it has to satisfy additional relations, namely the Young symmetry with respect to GL, the GL group. And so, for example, for the simple case of the hook, what does this Young symmetry look like? Well, first we can depict this diagram by a polarization tensor with two symmetric indices mu1, mu2, separated by the index of the box of the second row by a comma. So lambda is associated with the second box over here. And so the Young symmetry of this hook takes this form, namely complete symmetrization of all indices of the hook should be equal to zero. And intuitively, we can understand this as being the way to differentiate the state from the fully rank 3 symmetric now tensor, where this box would be in the first row. And so a general string state we can think of as an SOD minus one irreducible representation. So first of all, one would start with the GL reducible representation on which the general Young symmetry would look like this, then impose tracelessness on it, so the general condition would look like this, to reach SO, so from GL D in D spacetime dimensions go to SOD, and then additionally imposing transversality so that the tensor B transfers, one would arrive at SOD minus one. And I'm assuming for the rest that all tensors concerned that we're treating here are by construction transfers already. And so the point is that this general diagram or tensor, it has some free indices, and to construct to embed it in the string spectrum, to construct string states that have this diagram as polarizations, there's infinitely many different ways. So there's infinitely many different ways to contract these indices with alpha minus one, alpha minus two, etc. So all the possible string oscillators that are creation operators, and still embedded the diagram in the string spectrum at different levels up to multiplicity. And so our first question is, what is the simplest way that such a Young diagram can have its indices contracted and the diagram be embedded in the spectrum? And so for that, there is a very simple recipe due to Weinberg and I think literature around the same time, according to which the simplest way to embed a given diagram in the string spectrum amounts to contracting all boxes of the row I with the oscillator alpha mu minus I, namely the one that brings I units of energy in the mu direction. And so, for example, for a 3-row diagram, we would have all boxes of the first row contracted with alpha minus 1, all boxes of the second row contracted with alpha minus 2, and so on and so forth. And so for the hook, that would give us this very simple polynomial. So alpha minus 1 contracted with the mu1, mu2 indices, and alpha minus 2 contracting the new index. And we can very easily count the level of this polynomial. It would be 1 plus 1 plus 2, so 4. And indeed, if we go a few slides back, we see that the hook at level 4 is given precisely, that this polynomial embeds the hook precisely at level 4. And more generally, this prescription, it's straightforward to convince oneself that it embeds all possible diagrams to the lowest possible level where they can be embedded. So using the Weinberg recipe, embeds all Young diagrams allowed by SOD minus 1 to be embedded at the lowest possible level where they can. So the simplest polynomial minimizes the mass level. And so any diagram we can think of as appearing at this lowest possible level for the first time as the level increases. So there we can use the Weinberg recipe to construct immediately its polynomial. And we may also think of it as appearing very many, infinitely many more times at higher levels, n, which will differ by this lowest possible level by an integer w. And so at every higher level, which can be which are infinitely many, there's a new polynomial. So infinitely many possible polynomials can be constructed for the same diagram. But because every time for the simplest simplest class of diagrams, every time a new row gets added to the diagram, a new oscillator is contracted, it made sense for us, so Yevgeny Skvortsov and myself, with whom I developed the technology for subleading Regge trajectories, which I will explain in the next few slides. Well, because of this observation that every new row comes with a new oscillator, for the simplest class of polynomials, it made sense for us to define the notion of a trajectory, because the subleading Regge trajectory was not even defined in the literature in the past, as the set of all diagrams that have a fixed number of rows at fixed value of this integer w. And so with this observation, we were able to split the entire spectrum into two parts, all depth zero trajectories consisting of all possible Young diagrams that appear at the lowest possible level where they can make sense. And there are infinitely many clones that appear, so clones in terms of the shapes of the Young diagrams of the polarization tensor of the respective states. And those clones appear at depths bigger than zero. And this integer depth can increase arbitrarily high, so it's not bounded, much like the level is not. And so with these definitions, we see now that the entire leading Regge trajectory is part of this depth zero part of the spectrum, but there's more. So for example, the two-row trajectory, the first branch of which starts with the antisymmetric tensor, it also consists of the first appearances of Young diagrams with two rows. And in fact, this is only, as I said, the first branch. So the first branch contains only one box in the second row. But here starts a new branch, which also continues infinitely high in mass level, which has two boxes in the second row. So we have infinitely many branches of this two-row trajectory. But because all this in the entire two-row trajectory consists of diagrams with two rows that appear for the very first time, we know exactly what the polynomial look like, essentially what the vertex operator of this entire trajectory looks like. And so it belongs to a depth zero, the depth zero part of the spectrum as well. And so now this integer w, it made sense for us to define to name the depth of a given diagram, because it parameterizes how deep inside the spectrum we are. So for example, this entire subleading Regge trajectory of symmetric recurrence tensors, which, as I mentioned, it's a clone of the leading Regge, but a truncated one, so it starts with a spin 2. Well, this entire Regge trajectory consists of diagrams that are two levels up, so 2 units of energy away from their respective ones in the leading Regge trajectory. And so this entire trajectory is a depth 2 trajectory of one-row diagrams. And likewise, this two-row branch of a two-row trajectory is a depth 2, is part of the depth 2 clone of this trajectory whose polynomial we know. And so now this integer depth, it's along with the measure, with the number of rows, it's a measure of how complex the respective polynomial is. And so then came a next important observation that we had to make. Actually, historically, that's not how we discovered this point over here, but it makes sense for me to define in this presentation already now, namely that with all possible combinations of the creation and annihilation operators alpha of the string oscillators, we can define only 3 spacetime scalars And these three objects, they generate an SP2K, symplectic algebra 2K, where big K is the range of indices, small indices K and L. And so with this algebra, we're able to split its generators into two, into lowering operators and raising operators. Essentially, for us, it makes sense to identify the lowering ones as those that also remove units of energy from the game. And the next important observation is that all these depth zero trajectories, the polynomials of which we know very well, they're actually annihilated by this choice by the lowering operators of the SP, which means that they are lowest weight states of this SP, of this symplectic algebra. And in particular, it's easy to see that, for example, the hook, if we consider the simplest polynomial which embeds it in the spectrum, the one that embeds it at level 4, as we discussed, well, then the two lowering operators of the symplectic algebra acting on the simplest polynomial, they check nothing other than Young's symmetry and they traces this respectively. And so this entire group of infinitely many states organized in a finite number of trajectories, all at depth 0, they are now identified with the lowest weight states of a symplectic algebra. And also, we were able to rewrite the general Virasoro constraints on a general function f, not tied to a certain level, Young diagram or trajectory. So these general Virasoro constraints that are precisely the ones that impose physicality of states in the string as linear combinations of, as these sums, better put, of only the lowering operators of the SP, if one makes the identification of the lowering operators of the SP as the one as we did. And so now we're able to recognize that in fact, that the entire spectrum splits in depth 0 and higher depth trajectories means that the spectrum splits in lowest weight states of the SP, of whose the polynomial we very much know, and the rest of the spectrum contains infinitely many clones with respect to the space-time symmetries of the constituent member states, whose polynomials are not known, which are exactly the ones where we will be able to extract in the following. And to perform this extraction, there's another important observation that we had to make, namely that all these string states, of course, they're irreducible representations. They correspond to irreducible representations of the little group of the spacetime Lorentz. But now the spacetime Lorentz commutes with the symplectic algebra we observed inside the Virasoro constraints, because they operate in completely different types of indices. This operates on the modes of the string oscillators, and this operates on the spacetime indices mu. And so, with this, we were able to use an important result from representation theory called Howell duality, which essentially tells us, under specific assumptions here satisfied, that when two algebras commute, so in this case, the symplectic algebra and the SOD minus 1, 1 spacetime Lorentz, so there is a typo here, this n should be a k, not to, so in this integer should not be confused with a level. So whenever these two algebras commute, or more generally, whenever these two algebras commute, then in the oscillatory representation, their irreducible representations are maps in a one-to-one fashion, which means that we can employ all this to construct an entire technology of excavating clones of trajectories that appear at depth 0. So how does the technology that we developed work? You start with any trajectory of a depth 0, the polynomial of which we know exactly what it looks like. Now, this trajectory is the lowest weight state of the symplectic algebra, but if you dress it with the raising operators of the symplectic algebra that carry units of energy equal to the depth you intend to reach, then this entire ansatz is a candidate for the clone of this trajectory at this higher depth, at this deeper part of the spectrum parameterized by the W. And so now, if you impose the Virasoro constraints on this entire ansatz, which are just L1 and L2, and solve, for the a priori arbitrary coefficients, then you can excavate the entire clone. So how does this look like schematically? Well, again, let's go back to only the symmetric tensors, symmetric rank S tensors. And here we're in the spin alpha prime m squared plane. Well, as we had at the beginning, we had the leading Regge trajectory, so spin S stays at level S. But now we can parameterize all its infinitely many clones by this integer number W. So over here, we have a clone of the leading Regge at depth 2, and over here, we have a clone at depth 4, over here, clone at depth 3, and so on and so forth. But this is only an observation at this point. And so now let's use the technology that I developed with Yevgeny Skvortsov for the open bosonic string. And in particular, let's use this algorithmic procedure. Namely, let's start with the polynomial of the leading Regge, dress it with all possible oscillators that, not oscillators, erasing operators of the symplectic algebra that contribute at depth equal to 2. This amounts to only exciting SP6 raising operators, as can easily be seen. And then for this ansatz, solve the Virasoro constraints and you extract this entire clone of the leading Regge. And this can be performed in principle as for W as deep inside the spectrum as possible, because it's precisely this duality by how that guarantees, because we start with the lowest weight state, we can cover the entire spectrum this way. And the symplectic generators, they do not touch the form of the Young diagram, so it's always a spin S state that we embed with the spin. So for example, for the leading Regge trajectory in its first clone, let's see how this works. We start with the leading Regge over here, so just an rank S symmetric tensor contracted with S copies of alpha minus 1. Then it's easy to see, using the definition of the raising operators of the SP, that only these three combinations can enter at depth equal to 2, so only these carry 2 units of energy. We insert a priori arbitrary coefficients in front, and now solving the Virasoro constraints for this entire ansatz, very simply yields the coefficients as a function of the spin S. So D here is the number of space-time dimensions, which is known. It's 26. All this is implicitly in the critical string. There is only one free parameter in front, theta 1, so there is only one trajectory. And in this parameterization, the spin tells us how the parameters depend on the spin, tells us how the trajectories, with what kind of member states the trajectory starts. So this divergence at spin 0 and spin 1 is exactly what tells us that this clone is truncated. And now we see the point of truncation precisely as at the point where the beta coefficients no longer diverge. And because the spin is not free, the entire trajectory is known. And here I give you the simplest example. So the lightest massive spin 2 of the leading Regge and how the lightest massive spin 2 of its very first clone at depth 2 looks like. So we see immediately a simple example of how much more complex the polynomial looks like. But the point is that in a completely covariant way, the efficiency is increased by a huge amount. In some sense, infinite, because by solving the Virasoro constraints only once, we manage to write the solution as a function of this free parameter, of the spin being a free parameter. And so now the entire clone is accessible if we plug back into the ansatz. And this is very simple. So the polynomial now of the entire clone is extracted. And so let me very quickly summarize. With Yevgeny Skvortsov, I developed a technology for the open bosonic string case. We were also able to obtain a formula for a generalized Koba-Nielsen endpoint factor, which can be used to construct, in principle, any kind of tree-level amplitude, and we have several three-point examples. With Thomas Basile, I developed a technology for the case of the open superstring in the critical dimension, and especially in the Raman sector, this is highly non-trivial compared to the open bosonic case. And now with Thomas in work to appear, we have managed to extend to the closed bosonic string case, where again we see a non-trivial extension of the open bosonic string case. And in the meantime, I've also been working on aspects of black hole modeling, essentially the modeling of Hawking radiation from black holes in string theory, from deep string scattering, so scattering amplitudes of deeper clones. Another question is to develop the technology around other vacua. And with this in mind, let me also mention some future directions, namely whether the symplectic algebra can be related to the spectrum algebra that Gaberdil and West have discovered in the case of the closed string, so an algebra that is a symmetry of the closed string spectrum, which is not the case for the symplectic algebra because it is only a spectrum generating algebra. Then another question would be how the closed string case could inform the double copy and more generally the KLT kernel. Another question would be, given the amazing efficiency of this technique and also the fact that it's covariant, whether it can be used to construct also the known spectra of ADS spacetimes. And finally, now, because it offers access to scattering amplitudes, the next question would be to apply it in order to test the uniqueness and rigidity of string theory itself and its amplitudes. So with this, let me conclude by leaving you with a question, namely, how well do we really understand the underlying principles of string theory, and also with a note, namely, that its deep mysteries may lie in its massive spectrum. And with that, let me thank you very much for your attention.